Water is nearly 1,000 times denser than air. It relentlessly crushes hollow objects, and its viscosity generates massive friction against anything trying to move through it. The ocean rejects terrestrial machines. Because of this hostility, the first military submarines were not true underwater vessels. For the first half of the 20th century, they were essentially surface boats that possessed the mechanical ability to temporarily hold their breath and hide beneath the waves. You can see this compromise in their architecture. Early models featured flat wooden decks for the crew and high, sharp bows designed to slice through surface waves rather than glide under them. Operating this way carried severe penalties. Beneath the surface, these hulls generated tremendous hydrodynamic drag. They were agonizingly slow, they were acoustically loud, and highly vulnerable if kept submerged. As radar and sonar technologies rapidly advanced during the World Wars, anti-submarine warfare became increasingly lethal. Briefly ducking out of sight was no longer enough to keep a crew alive. To survive modern naval combat, engineers had to completely abandon the traditional boat concept. They needed to conquer three massive physical barriers: hydrodynamic drag, oxygen starvation, and deep ocean scaling. Moving quickly and quietly through a dense fluid means eliminating every unnecessary angle. The flat decks and wave-cutting bows had to be stripped away to prioritize pure hydrodynamic efficiency. In 1953, the United States Navy launched an experimental vessel called the USS Albacore. It was the first military submarine to utilize the lion shape, better known as the teardrop hull. Unlike a conventional boat, the teardrop features a continuous, rounded, three-dimensional curve. This shape minimizes water resistance and drastically reduces flow turbulence. It made the vessel difficult to handle on the surface, but it maximized speed and agility while submerged. Comparing layouts, Western designs use a single pressure tube enclosed by a teardrop shape. Russian engineers favor a double hull approach, placing the primary tube inside a larger outer casing. This gap provides massive volume to store fuel and ballast tanks without crowding crew living quarters. The teardrop hull turns submarines into highly efficient underwater missiles. But physical speed provides no tactical advantage if the power plant inside suffocates without access to the atmosphere. Conventional diesel engines require oxygen to burn fuel. For decades, this forced submarines back to the surface or up to snorkel depth to run their engines and recharge their batteries, instantly exposing their position to enemy radar arrays. Nuclear reactors solved the oxygen problem by splitting atoms to generate heat, but they introduced a different flaw. Most naval reactors rely on massive mechanical pumps to constantly circulate coolant. Those pumps generate a continuous acoustic signature, making the submarine detectable to hostile sonar arrays. Engineers attempted to build non-nuclear systems that could operate entirely without atmospheric air. Early prototypes, like the experimental X-1, relied on highly concentrated hydrogen peroxide to fuel Walter steam turbines. It provided rapid underwater speed, but the fuel was highly volatile and prone to catastrophic explosions. Modern air-independent propulsion, or AIP, solved this volatility. By utilizing closed-cycle diesel engines that safely recycle their own exhaust, or chemical fuel cells that quietly combine stored oxygen and hydrogen, these systems allow a non-nuclear boat to generate electricity entirely submerged. The German Type 212 serves as a modern benchmark for this technology. By utilizing a safe hydrogen fuel cell AIP system, it can remain deeply submerged and fully operational for weeks at a time without ever raising a snorkel. Because these chemical systems have virtually no moving parts, they produce almost zero noise. AIP technology created a new class of highly lethal coastal predators capable of ambushing the most advanced nuclear vessels. While AIP boats dominate the coastal shallows, the deep ocean required a different extreme. Delivering a strategic deterrent meant engineering a way to pack a massive payload of intercontinental missiles into a submerged, pressurized tube. The most extreme scaling solution ever constructed is the Soviet Project 941 Akula, widely known as the Typhoon class. The raw metrics of the Typhoon stretch the limits of marine engineering. At nearly 600 feet in length, it displaces 48,000 tons of water when submerged. To achieve this size, engineers abandoned the single cylinder, arranging two parallel pressure hulls side by side inside the outer casing. This wide stance fits 20 vertical ballistic missiles. The vast empty spaces generate extreme reserve buoyancy to punch through Arctic ice and even allows for swimming pools. The Typhoon class proved that physical constraints on volume could be shattered. It turned the submarine into a self-sustaining underwater city armed with apocalyptic firepower. The modern military submarine has completely severed its ties to the surface. It evolved from a compromised boat into a highly specialized marine organism. Today's naval supremacy rests on two extremes: the tiny, silent AIP coastal hunter and the colossal multi-hulled ballistic giant patrolling the deep ocean. By engineering precise solutions to hydrodynamic drag, oxygen starvation, and immense scale, human ingenuity conquered the abyss, transforming the depths of the ocean into the ultimate strategic battlefield.